I want to start with that because I keep reading this circuit and it keeps disappearing. So now it's there. Let's do that. So here you have a circuit, okay? And you see you have the power supply, and here you have 3 branches. So those 3 branches, you know how you do it, right? You follow along. Here you have an intersection. So that means this part here is in parallel. Do you agree with that? And then it combine that, they combine together, and then they come back to base, okay? The question to you is the following. You see here, the switch is not closed, the switch is not closed, okay? And you can measure the current here, which is 2 amps. How did you do it? How can we find that? We use Ohm's law. So if you just consider that circuit here, because you know the other one are not closed, what's going to be the equivalent resistance here in this circuit? What's the equivalent resistance here? 30. Okay, they are in series. Nothing is flowing through this branch and nothing is flowing through this branch. So how can I find the current? So the equivalent resistance is 30 ohms. The power supply is 60. So what's going to be the current? 2 amps. Okay? Do you agree with that? You can even find the voltage across the 20 and the voltage across the 10. The voltage across the 20 will be the largest because for the same current, the voltage is proportional to the resistance. Okay? So for example, if I if I measure the voltage here, you get 40 volt. Do you see? Okay? And if I measure the voltage here, I get 20. So for the same current, if you divide the resistance by 2, okay, the voltage is divided by 2 for the same current. Okay. So when you have a circuit in series, the equivalent resistance, so what did we say the equivalent resistance is? The equivalent resistance is 30. So you see the equivalent resistance is always larger than the largest resistance. So the largest resistance is 20, the equivalent resistance is 30. So when you have a circuit in series, the equivalent resistance is always larger than the largest one. Now, for a circuit in parallel, it's going to be the opposite. So let me ask you the following question. If I close the switch here, and if I close the switch, so now what do we get? So I close the switch. Do you see it's flowing through here? You have an intersection, so you're going to have some current going here, some current going there, and some current going there. So this is a circuit in. Okay. My question is, if you measure the currents now, okay, produced by or drained from the power supply, is it going more than 2 or less than 2? Think about it. So you see here you have, it's like instead of having 1 highway, you have 3 highways. So what do you think the equivalent resistance is going to be here? You have 10 and 10 and 10 in parallel, yeah? It's going to be what? Very good, 3.3, okay? So 3.3 repeating, is it more or less than we had like before? Less. Before we had 10, now we have 3.3. So when you have a circuit in parallel, the equivalent resistance is always smaller than the smallest one. So if you have 10, equivalent resistance is 3.3. So what do you think? So instead of having a resistance of 10, now I have a resistance of 3.3. So what do you think is going to happen? The current will be more or less than before? More, very good. It's going to be more, 2.7. Okay, why is that? Because you have decreased the resistance of this component of the circuit. So each time you have a circuit in parallel, okay, it decreases the resistance. The total resistance of this part here will be always smaller than the smaller one. So again, if I open here, nothing move. And if I open here, so now I have 10 ohms, and now the current is 2. If I close here and I close there, you see the current is 2.57. So you can imagine that if you have a 3 ways highway, okay, so if you have 3 lanes in a highway, okay, the car will be able to flow faster than if you just have 1 lane. Do you understand? Okay, so let's do it numerically. Let's find the total resistance, the equivalent resistance. So first you combine them together, and what do you get? 3.3 repeating. Okay, so this is inside like a bag, it's a black box, okay, and then it's in series with that 20. So what will be the equivalent resistance? Very good, 23.333. And if I want to find the current drain from the power supply, you're going to do 60 divided by 23.33333333, and what do you get? Huh? Very good. What's your name? Mattel. 2.5666666. Do you see? So if I ask you a question like that for a conceptual question, you will know. By closing these branches here and that one, it's like the current, can flow faster. Okay, there is no traffic jam. Okay, because now it has 3 lanes to go through. So I'm going to decrease the equivalent resistance here. Okay, so instead of having just 10, I'm going to have 3.333. Okay, so if I ask you a problem like that, you will know how to do it. Is that clear? So once you have the current here, you can find the voltage drop across the 20 ohms. So you do 20 times 2.7. You get something like this. It's just it depends where you put your drop. Okay, doesn't matter the sign. So that will be 51.43. And what's the equivalent here? Resistance? We said 3.333. So if you want to find the voltage across that component, you will say 3.33333 times the current. Okay, so do 2.57 times 3.3333333, and you get something 8.57, something like this. Do you all agree? Okay, so those two components, so this thing here and that thing here, they are in series. Okay, just to want to make sure that if I ask you for conceptual question, you will know. Okay, so that's for the test. Okay, so that's from the homework, something like this, and people got confused because just the way it's drawn. Okay, so just the way they draw it. But you see, if you go from here, okay, now you have 2 pipes. Okay, so it's an intersection. So you have 2 branches. And then you follow along. And okay, you're going to make like a turn. But is there an intersection here? No, it doesn't split. You have the pipe. Imagine this is a pipe and the pipe stay one pipe. If it stays one pipe, that means it's in series. So do you agree that the 10 and the 20 are in series? And the 5 and the 10 are in series? Okay, so let's find the equivalent resistance of the whole thing. Okay, so don't be confused because that makes like a weird angle. You can change it, right? It's still a parallel. They're in parallel, right? So you have two branches, one branch here and one branch there. Okay? So let's take care of this branch. Okay, you see there is no intersection. It's just following through. So this 5 and this 10 are in series. Very good. So 5 and 10 is going to be 15. So I have a 15 at the top, and here 10 and 20, they follow each other out. Okay, there is no intersection. So what's the equivalent? A 30. So I have a 15 and a 30. So what's going to be, and they are in parallel with each other. So that's going to be what? 10. Are you sure? You're positively sure. Okay. So 30 to the minus 1 plus 15 to the minus 1, boom, to the minus 1, boom. You were right to be positively sure. So the whole thing is 10. So what do you expect the current to be? 2. Okay? So the current is 2. Do you agree? Okay. Can you find for me the current in this branch here? Just the current in this branch. So let's see. Do we have the voltage across here? Between here and there? It's gonna be 20. Very good. You see? This one is connected to the minus. This one is connected to the minus. So if you want to practice, you can go back to the video and try to do the schematic like I showed you before. So maybe that will be helpful. But here it's 20. And what's the equivalent resistance? 15. So what's going to be the current? 1.3 repeating? Yes, you're right, because you do 20 divided by 15. Yes? Do you all agree with that? Okay. Now, if I want to find, and I try, if I want to be tricky, okay, I want you to find the voltage across the 5 ohms. There will be a question like this, okay? You have a point A, B, C, D, and you want to find the voltage across the 5 ohm. So between point A, say, and point B. You already have the current, yes? So how can I find the voltage across the 5? Exactly, you do 1.333 times 5, and you get 6.67 volt. Is that clear? So if I want you to find, so if I say the energy consumed per second, or the energy converted to heat per second, that means what? That means power. Okay, power is what? What is joules per second? So if you were to find the power converted to heat by this load, you will just multiply, for example, the current 1.33 times the voltage, right? Or you could do V square over R, or you can do RI square. Yes. Agree? Okay. So let's find the current here. So what's the voltage across those two? It's back to 20, yes? And what's the equivalent resistance here? 30. How much is 20 divided by 30? 0.666666. Yes? So if you want to find the voltage across the 10 ohms, all you have to do is 10 times 0.66666, which is 6.66666. Is that clear? Now, you have the video of this lecture, so you can always go back, do a schematic, find the best way for you to understand, and make sure you open your textbook. Okay, so I wanted to make sure that you know how to do this one. Okay. I will still review, but I wanted to make get out, because I've been 10 times I've been doing this over and over again. Okay, so where we were, go away. We were at AC voltage. So AC voltage, that's the voltage we get from the outlet. So if I ask you for the test, if you take a voltmeter, okay, and plug that into your outlet, so you have the hot wire and the return path, so you plug your voltmeter inside, okay, you're gonna get what is called the RMS, okay, so the root mean square voltage. So it's like an average. So what's gonna be your reading? 120 volt AC. 120 volt AC. Which means that your hot on or the hot connection will be plus, minus, plus, minus, plus, minus. But the peak value is not going to be 120, it's going to be more, right? I will show you how to do the computation. It's going to be 170 volt. Okay, so just let's review AC. I have an AC power supply here. I just have to close my circuit. I don't know why. I think this app does not like me anymore. Everything I try to do something get messed up. Okay, so what do you see here? What's happening to the light? On and off, right? It makes sense because you know the current is going to be positive, get to zero, negative, get to zero again. And I can use this here. You see the current is it's not cooperative today. So you see up and it goes to zero, negative. So it's going to follow a sine wave. Okay? So let me ask you something. Since most of you are in biology, how come I don't see the light flickering here? Do you remember the frequency of the electricity that we get? 60 hertz, right? So it's gonna go one way, the other way, 60 times in 1 second, right? So one cycle is 0.02 seconds. So it means go back and forth, back and forth, back and forth, back and forth, 60 times in 1 second for the electricity that we get here. And the voltage is going to go up and down, up and down, up and down, 60 times per second. So why do you think we don't see the light flickering? Very good, too fast. So if you study the human eye, it takes, it's gonna print in your eye and then it will stay for a while. So but before it refresh, right? Yes. Very good. That will be a good idea if you want to do that for a demo. If you have, I don't know how to do it. Okay, I don't understand this thing, but if you have you can do it with a smartphone, and you can take a video of the light, and then you slow it down, and you're gonna see the flickering. You can even compute how many times does it go on and off in 1 second. You should find about 60 times. Okay. So if I put the voltage here, so this is not 120, it's something smaller. I don't know what it is. Okay, it's about RMS should be about 5 volt. The peak value is 10. Okay. How much is 7? No, I know, you know what? What's the peak value here that you see? 10. What's the RMS? The RMS will be 70% of the peak value. So in that case, it's going to be 7 volt. So what does it mean? It means you take your voltmeter, you measure across here, okay, in a real life, you're going to find 7 volt RMS, but the peak value is higher. It works the same here for current. You see the peak value is what? 1 volt. So the RMS will be 0.7 volt. Very good. Okay. And why do we need those RMS values? It's because we can use Ohm's law. V equals Ri will hold for AC circuit only if you are using RMS. Okay. So you see how it's going back and forth. So I don't know if I have like uh, simulation. Okay, I found this one that I like. Even though a battery, a battery is not, it cannot provide the AC circuit, but you see what's happening to the hot wire. You see how it's plus and then becomes minus and then it's plus, right? So the voltage increases to 170 volt and then it goes to 0 and then to go to minus 170 and then go back to 0 because the hot wire that you have in the plug switches 60 times per second. Okay, so the current is flowing in one direction, the other direction. So it's going back and forth 60 times in 1 second, and the period is 0.02 seconds. Okay, I just close everything. Good. Here you can see that here. So here they are showing you the current. So you see here the peak value is 0.2 amps. But can you tell me what's the period about? 0.02, okay? So that will be the time it takes for one cycle. The time it takes from the hot wire to go from plus and then minus and then back to plus. 0.02 seconds. So 0.02 seconds, it's the period that we have here from our outlet. And how do we find 0.02 seconds? We do 1 over 60. Okay, so 1 over the frequency is equals to the period. And so someone asked, how come you have this frequency here? I just close again. You see, because inside the power plant that is producing electricity, you're gonna have, it's like an electromagnet, okay, that moves, okay, and that will create that AC voltage. And if it's going in and out 60 times, that's why the voltage will follow a sine wave and with the frequency of 60 hertz, it's called. Is that clear? Actually, in the real life, but we'll see that next. It looks like something like this. Okay, so you burn some fuel, so it could be coal, or it could be natural gas, or it could be nukes, uranium, and there is a turbine that is spinning at a rate of 60 cycles per second, and that's how you produce this AC voltage and AC current. Okay, so here we go. So I try to summarize everything here. So the frequency from the outlet is 60 hertz, so 60 cycles per second. The period for one cycle, so once this is one cycle, it starts from here, 0, 170, 0, minus 170, go back to 0. That will be the period, about 0.02 seconds. How do you go from the frequency to the period? The frequency is 1 over the period. Is that clear? So if I ask you for the test, if you go to Europe and the frequency is 50 hertz, which it is, how do you find the period? 1 over 50, okay? So AC doesn't work the same way. Plus in Europe, the RMS is 220 volt. Here, the RMS is 120 volt. So in Europe, they have a higher voltage. So that way, they don't need that much current, so they can save with the copper that they use in connecting wires. Okay? So again, the RMS, okay, that's what you measure with your voltmeter, which is equals to 0.7 times the peak voltage. Okay, so if you isolate the peak voltage, you get 170 volt. Okay, so if you want to make a drawing, I think it's in the pop quiz, you always, for a sine wave, you always have the peak value here in front. Okay, so the peak value is 170. Here you have sine or cosine, doesn't matter. And you always have 2 pi x. X will be the time, so it's the variable, okay, because it makes a function. Okay, so that will be f of x, that will be your x. You always have 2 pi x over, and here you have the period, which is 0.02. Is that clear? So a little bit of connection with math, not that much. Example, here, what's the peak value? 10. Okay, what's the period? So it's go one cycle up and then go down. That will be your period. 5. Okay, so that will be the equation. Now, if we want to find the frequency, so you see how it's very slow. So it doesn't vibrate very much. In 1 second, you don't have a lot of cycles. How do we find the frequency? So you have the period is 5. So how do we find the frequency? 1 over 5. Okay, so that will be 0.2 hertz. Okay, it should be cycles per second, but we like to confuse students who we say hertz. And it's just because Henry Hertz, he's the one who detected for the first time electromagnetic waves. So we had to give his name to one of the units. So, okay, we pick cycle per second, and our student it's not cycle per second anymore, it's going to be Hertz. That's for the story. Okay, so just a review of waves. You see, if you have a wave, so here you have a pebble here, and it's going to make waves that move away from the source. If you take a picture at a given time, the distance between two crests is called the wavelength. Okay, so if you take a picture, so for a given time. Now, if you are a given location, so here you have a bug, okay, on the surface of the water, the bug is going to go down and up and down and up. So that will be the period, okay, the time it takes for the bug to go down and then up and then down again. So a full cycle will be the period. Okay, so it's just a connection to waves. Because I think for the MCAT, you do have to go over wave and simple harmonic motion. So I have like a playlist about that. But that's how it's done. You have an AC generator here. So you're going to move like a magnet inside the coil. And that's how AC is produced. Okay, any question? So again, this is the peak value. So here we have 170 volt. This is what we call the RMS. So it's some kind of average, and that's what you will be measuring with a voltmeter. Okay? So I don't know if you do that with the lab. I don't think so. I don't think the lab are zip it. So no, I don't think you're gonna use an oscilloscope. But if you were to use an oscilloscope, that's what you'll see. Okay, you see the voltage changing with time. Okay. Okay. So let's do this one. So remember, so this this device does not need DC. It cannot work with DC. So all you have to do is to turn 120 AC to lower voltage AC. It needs to work with AC. Okay, so you don't need DC. Unlike my laptop, for example, my AC will be turned into DC. But in that case, no. So the idea here is that you can use Ohm's law, like we did before, as long as you use the RMS. So here you have the power supply, okay, is 34 volt, but that will be the peak value. So can you find the RMS first? You need to find the RMS voltage, the RMS current, and the RMS and just the average power. Okay, so you can use Ohm's law like we did before, as long as you get the RMS voltage and you are using the RMS current. Otherwise, you can't. So I RMS will be equals to square root of 2. Actually, so I'm going to simplify 0.7 peak, the peak value, and V RMS. That's the one that you can use. Those two you can use for Ohm's law equals 0.7 V peak. Peak. Okay, so you have a peak value of 34 volt. So what's going to be the RMS? 23.8. Do you all agree with that? Okay, you take 70%. So 23.8. I'm going to say 24 volt AC. Okay. So now I can use Ohm's law. So you have a resistance here, it's 8 ohm. Okay, what's going to be the current? So if I use the voltage, the RMS voltage, I will get the RMS current. That's all. So that's going to be 3, you sure, right? Yes, you're right. So that's going to be 3 what? 3 amps. Okay. And the current is going to flow one direction, the other direction, one direction, the other direction. Okay? Now the power, okay, used by the load and produced by the power supply. Okay? So in that case, I have to use the RMS values. Okay? So it's going to be 3 times 24, which is 72. Huh? 72 or no? Okay. 72 what? What? Very good. What? Okay? So that's how much power is consumed by the load, how much power is produced by the power supply. So I suppose that somewhere, it's connected here to 120 volt AC. And this here, inside, you have some kind of transformer that will turn that into 24 volt AC. Okay, so it's going to bring down the voltage. Is that clear? Talking about power, if I say joules per second, it just means what? Is that clear? Okay. So if you use your textbook, the real equation is V RMS, for example, equals, it's 1 over square root of 2 peak. And if you do 1 over square root of 2, that's about 0.7. Okay? So you can even say that the peak value equals square root of 2 of the RMS, or 1 over 0.7. That's the real equation. Is that clear? Right? Any question? Good?
At the top, why did you put the VRMS equal to 0.7?
Because that's the definition of the current, RMS current. So RMS current is 0.7, but here you didn't use it, right? Because you use the Ohm's law. However, if I want to find the peak, how can I find the peak? I will say it's 3 times or divided by 0.7. So what you get? 4.8. Okay, 3 amps. Okay, do you understand? So what does it mean? It means that your voltage, the voltage, okay, as a function of time, it's gonna increase. What's the peak value? To 34. And then it goes down, and then it goes up, and then it's gonna make a sine wave. Because it's connected to your outlet, then the frequency here is the same, so the period is about 0.02 second. If you do the current as a function of time, what's going to be the peak value? 4.3, and it's going to go up and down and up and down, right? And the cycle is still 0.02 amps. Yeah. No, because I say it's connected to the outlet, so the frequency is 60 hertz. Okay, so the period is 0.02 seconds. It's going to be the same frequency even though you bring the voltage down to 34 or to 24 volt AC. Okay, any question? So conclusion, here you have it, okay? The voltage RMS, the RMS voltage, okay? That's what you measure with your voltmeter. That's what you use for Ohm's law, equals 0.7 times the peak. The peak meaning this, okay? And the same thing for the current. Is that clear now? Okay, so if you plug that oscilloscope, for example, to the outlet, you're gonna see that here, what's gonna be the peak voltage again? 170 volt. What's gonna be the period? 0.02 second. What's gonna be the RMS here, which I measure with a voltmeter? It's gonna be 120 volt. Is that clear? Okay, that's how it works. Now you can do the same thing with the current. So how many cycles do you have in 1 second? No, from here. So it's gonna be, what's the frequency? 60 hertz. Okay? Is that clear? I can close the file. Any question? You sure? Okay, about let's go back to reviewing. So what's the outlet here? RMS, it's 120. What's the peak value on top of the sine function? 170. Very good. What's the period, the time it takes for 1 cycle? Very good. And what's the frequency? 60 hertz. Okay? If I ask you, let's say you have two light bulbs. You have a 40 watt and a 60 watt that you go buy, in a hardware store. Which light bulb will be the brightest? The 60, right? It's going to be brighter. Of course, it's 60 watts. Come on, it's consuming more energy. 60 watts means 60 joules per second. So, therefore, both of them, I'm going to connect it to the 120 volt. Okay, so 120 volt. Okay, so the voltage will be the same for both, but the 60 watt will be the brightest. Okay, so it means where is the largest current? For the 60 or the 40? 60, because it's the brightest, right? Power equals V times I. So this is the same, 120. So if it's consuming more energy, that means the current is the largest, right? So if the current is the largest here than there, which one? So that means here you have a large current, and here you have a smaller current. So which one has the largest resistance? A 40 watt or a 60 watt? 40 watt, very good, has the largest resistance because it's like squeezing the pipe. You imagine it's a pipe, okay? So you don't have that much current flowing. It's going to resist more. So this one has a small resistance and, no, what did we say? Larger resistance, and this one has a smaller resistance because you have the large current and here you have a small current. Does that make sense? Right? So if I ask you which one will be the brightest, it's going to be the 60. Which one has the largest resistance? It's going to be the 40. Now, if I do something that we never do, so if I have the 40 watts, so it's a big resistance, and then I put that in series with the 60 watt, which has a resistance. So this is R, that is a big R. And I connect them in series with 120 volt that you should never do. Surprisingly, so it's going to be the same current now for both. Okay. Before it was the same voltage, now it's the same current. So where is it that will have the most voltage drop? The 40, because it has the largest resistance. Okay, remember we discussed that? So this one will have the largest voltage drop. Okay, so which one will be lit? This one will work and this one will not work because it doesn't get enough energy. So Ohm's law says that the voltage drop equals sorry, Ri. Okay, so for the same current, if R is big, the voltage will be big. So this one is taking everything. Okay, any question? So this is a reviewing for the test. Okay, another question that sometime. So if you are not convinced, do what I did when I discussed that. I already discussed that. Do what I did. Make a circuit in series with the simulation. Take a 10 light bulb and a 20 light bulb, okay, ohms. Connect them separately and connect them together and see how the brightness will change and measure the voltage. You can do that on your own. Okay, so do you remember those circuits here? So I told you that inside batteries, okay, the batteries that you buy, 1.5 volt, 9 volt, 12 volt, etc., you have inside, everything happens like you have a small hiding resistance. And as the battery get older, that resistance is gonna increase. Which means when you have a current running, because here you have the load, so this is your load, okay? You have current running. This little sneaky guy inside your battery is gonna take away some of the voltage, okay? Some of the power. So let's take an example. Can you remind me what's going to be the voltage across a car battery? 12. Okay, so 12 volt. Let's say you have a sneaky guy of 5 ohms. Okay, and let's say you have current. So we don't know the load, but you know that the current flowing in the circuit, so it's flowing all around. Let's say it's um, oh, uh, 0.5 amps. Okay. Now, question is, how much energy will be dissipated by the resistance here, 5 ohms? So when you say energy dissipated per second or energy converted to heat per second, that means the power, right? So how much energy is being consumed by that little sneaky guy? 2.5 watts. 2.5 watt, right? So V times I. Uh, no. 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 What were? Oh. No. What is power? We don't know the voltage here. Oh, yes, we could find the voltage, right? No, you're right. Okay, what you are doing is the voltage. Okay, so you're right, 2.5 volt. That's what you said? So this is correct. You all agree with that? Because the resistance is 5 ohms and the current through it is 0.5. But I want the power.
When you're trying to find power, that's when you have to use watts.
Yes, so power is watts. That means joules per second. And the power, for power, you can use 3 equations. So V times I, so that will be true for anything. And if you have a resistance, you can say Ri squared or V squared over R. Okay, so you can do it step by step, or you can just use this one. So since you already found the voltage, I'm going to do V times I. So the power will be what? What's the voltage? 2.5 times uh, times 0.5. That's what you say? Okay, so what's going to be it? What? So that's how much power is being stolen by this resistance inside, and that energy will be converted to heat. So it means that battery, as it gets older, you see the resistance is going to increase, and your battery in your hand gets warm, okay? Because of that little resistance inside. Do you understand? Okay, so I could have used that equation instead. So if I do 5 times I squared, so that means 0.5 squared. So what you get? 5 divided by 4, which is 1.25 watts. Is that right? Okay. If I want to find the terminal, so that 12 volts is called the EMF. So this one is stealing 2.5. So how much is left for the load? So 12, yes, minus 2.5, which is, uh, what do you say? 8.5, right? 9.5, thank you. 9.5 volt. Okay? That's what happened when your battery died. Okay, you have to change battery. It's because the resistance here is so much that your load does not get the 12 volt it needs, but it's going to get less. Okay? Okay, that's it. Okay, now one more thing. Okay, plus you have the practice test for just to review. Um, okay, the other thing you want to very pay attention to is the unit. Okay, memorize the unit if you don't have everything in the equation sheet. So, for example, the current by definition is the number of charge, crossing a cross section, okay, in your wire divided by the time. So it's the amount of charge per unit second. Okay, so for example, if you have 3 amps, that would means 3 coulomb per second. Or if you want to find the current and you are given 5 coulomb for 1 minute, okay, so you will do 5 divided by 60, it's going to be the current. So pay attention to the units. So for example, watt is joules per second. So it's energy produced per second or energy consumed per second. Likewise, remember the beginning of the semester, the voltage is, by definition, energy per coulomb. So if you have a voltage of 9 volt, that means each coulomb, so 1 coulomb will get an energy of 9 joule. Okay? So each time you divide, okay, even in chemistry, those kind of equation, that means per unit. So energy per unit charge. Charge, so coulomb per unit time. Okay? So if you understand the unit, and you don't forget to print out your equation sheet. Okay, the test is on Tuesday. It's in person, it's on paper, no makeup. Like if you have an emergency, maybe there will be a makeup, but it will be always harder because I don't have 1 hour or 40 minutes office hours. So I have to cut the test in two, and it will be harder to get a good grade. So make sure you make it. If you have an accommodation through the GRC, you have to do it. Okay, you have to see them and secure the spot and blah blah blah. Okay, any question? No, good. Let's move on. Oh, okay, one more thing. Uh, so why is it important? For example, if you are doing biology, because that led to Nobel Prize. You can modelize a neuron or a cell with an electric circuit because you remember the voltage across a cell is due to the motion of electrolytes, right? So you have potassium, sodium, I don't know what it is here. L stands for what? I don't know. But you see, you can model that with a circuit. I don't know what it is. L. Sodium, potassium, chlorine, iodine. No, not iodine. Huh? I don't know. Okay, you know. Okay, let's start a new unit. Um, electrostatics. So, no. So we already, yes. No, you can history. We're gonna use it now. Okay, we're gonna use what we have learned back then, but no history in test one. So we already talked about that, the first class. So you have this model of the atom. So you have the nucleus here, you have protons, and what is in red? Neutrons, right? And all around you have electrons. So this is called the Bohr model, and it's not totally real because in reality electrons are on orbital, so it's not really true. But that's enough for what we need. So the first thing to remember is when an object is charged. So for example, I brought a balloon somewhere. I'm gonna rub it against my hair, for example, it's gonna become charged. That means either electrons are gained or electrons are lost. Only electrons can be transferred or moved. Not the positive charge. Positive charge, they don't go anywhere. Only electrons can be lost or electrons can be gained. Okay? So this value here is the fundamental charge. Okay, so that will be the charge of an electron and the charge of a proton. So it will be the same charge. You see, it's a small charge here. And here you have the mass of a proton, the mass of a neutron, the mass of an electron. Which one has the lowest mass? The electron. Okay, so it's about 10 to the negative 30. This one 10 to the negative 27. So it's about a ratio of 2000. So the electron is about 2000 times less massive than a proton or an electron. So in the periodic table, okay, when you are looking at the atomic mass, you don't take into account the electron. It's only the number of protons plus the number of neutrons that matters. Okay? The mass number. Okay, it's called the mass number. Okay. Now, another interesting thing is that between the nucleus and the electrons, so the closest electrons, so level one, you have a lot of emptiness. So if this was like here a basketball, the electron will be all the way over there. So it means if I have an electron here, I don't know, the size of a pea, a nucleus, sorry, nucleus the size of a pea, the electrons will go all around BBC campus. Okay, this is how much emptiness you have between the nucleus and the first electron orbiting the nucleus. Okay? So how come if I push the wall, I don't go on the other side? Because it's so empty, you don't see it with your eyes because you have very bad resolution. But all that matter here is empty, okay? Because you have a nucleus here and the electron very far away. How come I don't go through the wall? Huh? The what? So I have protons, electrons. It has protons, electrons. So electrons, electrons. So what's happening? They repel each other. That's the only reason why I don't go through the wall. Okay, because it looks to you that it's dense, but it's not. It's just our eyes cannot see very well. Now, if you look at physics quantum, like physics, quantum physics, it says if I keep pushing long enough, I will go through it. But I have to wait like a million years, so I will be dead before that. So example, let's say you have, so the ratio is 10,000. So it means the distance between the nucleus and the first electron is 10, 100,000 larger than the size of the nucleus. Okay? So let's say the nucleus is 1 millimeter. Let's change the scale. So let's say you have a nucleus 1 millimeter. So 1 millimeter. So let's say this is the nucleus. 1 millimeter is about this. So this is one. So let's say I make a nucleus here, 1 millimeter. how far will be the electron? The ratio is 100,000, so it's going to be 100,000 millimeters, right? And how many millimeters in 1 meter? 1,000. So that will be 100 meters. So if this is the size of a nucleus, your first electron on the first orbit will be 100 yards away. So this is how much emptiness there is in matter. Isn't that surprising? Yeah. It's just because our eyes have a very, very bad resolution. We cannot see really. We merge everything together, right? So the other thing interesting is that any charge will be always an integer number of an electron charge, which means, what does it mean? It means that you can have 1 electron, 2 electron, 3 electron, okay, lost or gained. You can have 1 million electron, you can have 5 billion electron, but you cannot have half of an electron. You cannot have 0.1 electron. Okay? So any charge, okay, so for example, I will soon, so for example, no, let me take a simulation. Okay, so we're going to talk about static electricity. So, so the balloon, what happened to the balloon? Did it gain electrons or did it lost electrons? Gain electrons. Can you see any half of an electron or 1/3 of an electron or 1/10 of an electron? No. So if I want to find the charge on that balloon, I will have to compute how many extra electrons that it stole from the sweater, okay? And I multiply by the charge of an electron, okay? So the charge of an electron is what? Uh, the charge of an electron is 1.6 times 10 to the negative 19 coulomb. How many extra electrons do I have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. This one belongs to here. So the charge will be 13 times 1.6 times 10 to the negative 19 coulomb. You see how it works? So now the sweater, what happened to the sweater? Did it lost electron or gain electron? Lost electron. So you see, only electrons can be transferred. Now let me ask you something. This balloon here, is it a conductor or an insulator? Insulator, which means if you apply a voltage, you're not going to have current flowing, right? So that's why those connecting wires, they have rubber all around them, okay? They are insulators. So can you see that those electrons, they don't spread out? It's like they are sticking here, okay? They cannot spread out because it's not a conductor. Do you see that? So I'll get back to that, but let's say let's do a problem. Let's do this problem here. So let's say you have a huge charge of 1 coulomb. So somehow that will not be, it's not possible, okay? But let's say it will be possible to put a lot of electrons here on on a balloon. So I take my balloon, I rub it against the air, for example, and I have some electrons here. And let's say now the charge is 1 coulomb. How many electrons do I have? And the charge of an electron is going to be 1.6 times 10 to the negative 19. So you need to find n. See what you get? So 1 coulomb, any charge has to be integer number of the fundamental charge. And the fundamental charge is the charge of an electron. So it's going to be 1 divided by, open the parenthesis, 1.6 times 10 to the negative 19. Do you get this? 6.2. Okay, so 6.25 times 10 to the 18 electrons. So don't tell me it's not an integer here. It is an integer because it's 10 to the 18. So that will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 electron. Okay, it's an integer. But you cannot have this 0.5 or 0.1. It's always integer. Okay? So that will be actually a minus. So here I just use absolute value, but it's negatively charged. Okay? The sweater I was rubbing against, of course, it's gonna it has lost the same amount of electrons. So now it's positively charged of 1 coulomb. And it has lost that many electrons. Is that clear? So now we are not in moving charges, we are in static charges, so electrostatics. Talking about conductor, okay? So if you have a conductor, like a metal, like copper, for example, or aluminum, that means that the electrons on the outermost layer, they can flow. Okay, all you have to do, you apply a voltage and the electron will flow. Okay, so that will be for conductors. So if you take a chemistry class, for example, that will be a typical metal like copper. It's like you have the nucleus of copper, nuclei of copper, you have electrons that are attached to their nuclei, but the outmost layer, the electrons from the outmost layer, which is called the conduction layer or valence electrons, they are free, to move, okay? They are not faithful to their nucleus. They are not attached to their nucleus, okay? They move around. Hey, how you doing? Hey, how you doing? Hey, how you doing? Okay, they can flow freely here. And you just have to apply a voltage for those electrons to start flowing, okay? From the positive electron to the negative electron. Okay, so that's how conductors work. Now you have what it's called insulator. Insulator, their electrons are very faithful. They don't want to leave their nucleus. So if you apply a voltage across a piece of paper, nothing will happen except if you put a huge voltage and you're going to burn the paper. But otherwise, the electrons are not moving, okay? They are not leaving their nucleus, okay? So they are very faithful, I would say. Now, it is possible to have those electrons moved if you do what is called charging by friction. Okay, so for example, if you take fur and if you take a balloon and you rub them together like this, okay, so I rub them together. Now you see the electron have been transferred from the sweater to the balloon, but the balloon is an insulator. Do you see those electrons moving away from each other? No, it's like they are glue. They cannot go anywhere. This is because they are insulators. What's happening here is that you are doing work. And by doing work, by rubbing against the two of them each other, okay, you are transferring electrons from the sweater to the balloon. You might ask, why is not the opposite? It depends, you learn that in chemistry, it depends on the affinity. So the rubber here has more affinity for electrons than the sweater. The sweater says, okay, go, I don't care, right? So I can show you that here. So this is here what we have. We have to check the time. Here it's called an electroscope. Can you see here? And you see here it can rotate. You see that how it can move? Okay, so this is a conductor or insulator? Conductor, very good. So that means electrons, if you put extra electrons on it, so right now it's neutral, but if I manage to put some electrons on it, are the electrons going to stay here or they're going to move? They move, right? They move as far as possible from each other. This is because it's a conductor. So I'm going to try to show you that. So this is what? Insulator or conductor? Insulator. So I have to do work. I'm doing work, right? So I'm transferring electrons from my shell to the balloon, right? So I'm charging the balloon. So the balloon becomes what? Positive or negative? Negative because it has more affinity. Are the electrons moving all around or they just stay there like a kite? Stay there. I'm going to try to force them to go here. Let's see if it works. Do you see how it moves? So now if I insist, once the electrons have been transferred on the top, they are not going to stay at the top. They're going to move as far as they can. So that's why the needle is being repelled. Isn't that cool? You see that? And we are lucky today because it's a dry weather. So when the weather is dry, you can keep the charge here. So you see it's a way to store charges. So it's like a capacitor, okay? It can stay there. So what can I do to uncharge it? Now it's being charged negatively. Yes, I can ground it, right? Remember, electrons always wants to go to the ground. So if I touch it, boom, it goes back to the ground, and then it's neutral. Isn't that cool? So this is what's happening here. So if uh, if you have fur and balloon or ebonite, it's a type of rubber. If you rub them against each other, you're going to transfer some of the electrons from the fur to the ebonite. So the fur will become positively charged and the ebonite will become negatively charged. So here there is an excess of electron and here you have a loss of electrons. Okay? Now, it's the opposite if you have silk and glass. So if you, and I will show you, but if you take a silk and a piece of glass and you rub them against each other, it's the opposite. Silk has more affinity for electrons, so the glass will become positively charged. Let's see if I have like a... Oh, by the way, you see, talking about grounding, you see, it told me if you touch with your finger, the electrons will go back to the ground. So that was
3 versus 138,000 volts.
You see what's happening? There is a tree that fell on the high line tension. And those lines here, they are not insulated, okay? So they find a path to the ground. And so it's like the air is ionized. It's a and of course, you know, it's like a short circuit, and the electric company is
3
losing
versus
a lot of money.
138,000 volts.
Isn't that cool? Okay. I want to do demos because I don't want to bring that back. So let me quickly here. Come on, come on. Okay, so we have here, it's negative charge. So what do you think what's happening here? So this one is not charged to begin with, right? This one you have plus here, minus here, so it's neutral. But when you bring close to it, you see, this is called polarization. I will explain. But anyway, once you touch it, it's going to be charged. See that? Now, if you have a glass here, so let's say you rub it with silk. Okay, so silk will take the electrons, so glass become positively charged, and boom. Okay, there is one more thing I want to explain. So, do you see the wall here? Is it a conductor or insulator? Like the wall? Huh? Does it, can you run electricity through it? Inside the wall, through the wire, yes, but on the wall. No, it's an insulator, right? It's not made of metal. However, you see those walls is here, it's made of the nucleus and the electrons here. So these are molecules. And if you bring the negatively charged balloon, what's happening? It's not that the electrons they can move, but they can be pushed away inside the molecule. Okay, so it's like they become a dipole, like the water molecule. So the water molecule has a plus on one side and a minus on the other side, and here it's kind of the same thing. So this is called polarization. Okay, so you see these electrons here are pushing those one. Do you understand? So it's very much like these are molecules. Okay, you have a molecules and you have a plus and a minus. So these are the electrons, these are the protons. But if you bring something negative, the electrons are going to be pushed away and the nucleus is going to stay here. So this is called polarization. It doesn't mean that the electron can escape. Okay, electrons cannot escape, but it's going to be pushed away. Okay, we'll talk about that more, but this is called polarization. Okay, so a typical conceptual question. And by the way, there is a lot of demo you can do. Like for example, you can build your own electroscope, like the one I have. You can build one here. So if you have fur and ebonite, or hair and balloon, which one is losing the electrons? The hair is losing electrons, so the hair becomes positive and the balloon becomes negative. So experiment, it doesn't work with me because my hair is color, uh, sadly, because I'm old. But with you, you are young. If you take a balloon like this one, you rub it against your hair, you're gonna see the hair coming like straight, right? Because the hair become positively charged. So all the hair here are repelling each other. So it's gonna be straight like this. Right? You already have experienced that when you remove a sweater, the hair goes up. That's electrostatics, right? It doesn't work with me, but you can do that for a demo, for example. So if you have a glass rod here, and silk is the opposite. The silk gain electron, the glass loses electron. So there is a transfer of electrons. Okay, so now I want to do the demo. So this is easy to understand. Positive and negative, do they attract or repel? Attract, okay? So it's like a north pole and a south pole. Negative and positive, repel. So let's see if we can do that. Uh, so this is silk. This is silk. And these are insulators, right? Can you see them? Okay. So I'm gonna rub it. And electrons will be transferred. I don't know which one becomes negative because I don't know the material, but electron will move from one to the other one. Okay, and I have to do work. Otherwise, electrons don't want to move. I have to force them to move, force them to be transferred. So then I'm going to put that here. Okay, and I'm going to do the same thing with this. Okay, I'm rubbing, I'm doing work. Electrons are being transferred. So what do you think is going to happen? Do they repel or attract? Ooh, isn't that amazing? Do you see? Minus and minus repel each other. It's a force at a distance. Okay, do you remember in physics one? How do we call that? It's a torque. Very good, right? I'm applying a torque, so there is a twist happening. If there is a torque, unbalanced torque, there is an acceleration. Very good, very good, very good. So now I'm going to take two different materials. So I have glass and fur. Okay, so now it's going to be charged the opposite charge. Okay, so you see it's not silk, it's fur. And I have to do work. So this one is negative charge, this one is going to be positive charge. So it's going to attract, let's see. Ooh. Isn't that nice? You see, it's like magic, right? It's a force at a distance. That's actually what's happening is that you have an electric field. So it's like a magic field on. It's fun, right? Okay. If I do that, it doesn't work too much now. Okay. So what do you think here? You have a plastic rod that's being charged up. Thank you. It's being brought to initially metallic sphere. Allow to touch the sphere in a few seconds. So let's say the plastic rod is negative. It's touching the metallic sphere. So the sphere becomes negative. Okay, the plastic rod is negative. It's touching a conductor, so it's going to become negative, like my electroscope I showed you before. So this is negative. The rod is then separated from the sphere by a small distance. After becoming separated, the rod is repelled. Okay, because the sphere is negative, the rod is negative, now they repel each other. Does it make sense? So this is what I did here. Electricity. So I think this is a metallic uncharged PIF ball. I don't know if it's conductor or not, but you see I bring in. It could be a conductor. Let's say it's a conductor. It's easier to understand like this. So now it's being polarized. The electrons are free to move, so they're gonna move away. And I touch it. Now it's being negative, so it's gonna be repelled. Do you see that? Like the electroscope. So about conductor. So if you have a conductor, the electrons are not going to stay where you left them. So it's not like the balloon. If you have a balloon, okay, you rub it, the electrons will stay wherever you place them. They cannot move freely. But if you have a conductor, the electrons that you place here, instead of staying there, they're going to move as far as possible from each other because they hate each other. Do you see electron inside? No. Okay, when you have a conductor, the charge always move on the outside, as far from each other as possible, as far as possible. So where is Travolta? You see, he's a conductor. So if he rubs his shoes against the carpet, what's going to happen? Electrons. Very good. So there will be a transfer of electrons. Okay. So in that case, it will be from the carpet to the shoes. But once the electrons are here, are they free to move? Yes, because he is a conductor, right? We are made of fluid. So the electrons here are going to move and they're going to move on the outside. If you wait long enough, when you reach static equilibrium, electrostatic equilibrium, they're going to move as far as possible from each other. Are they happy? Electrons? No. What do they want? It to be in the ground, exactly. Right? And if the voltage is high enough between the finger and the ground here, okay, you're gonna have a breakdown of the electric field. So it means the voltage is high enough that you're gonna ionize the air. That's the video I showed you before. Isn't that cool? Okay, and maybe I'll keep that for next time, but this is, have you seen that already in a science museum? It's called a Van Gogh generator. You saw that already? This one. We'll do more demo on Thursday,